Moore, and this is about powering the future. And we're really going to focus in on solar power. We're going to dig deeply into the generation of electrical energy, as I said, specifically about solar power. We will definitely tie in our earlier studies of DC circuits and the law of conservation of energy, as well as a discussion of generators, which is about electromagnetism, and photoelectric cells, which use the photoelectric effect. No matter what your career path is going forward, you are most likely going to have to be familiar with the ramifications and issues surrounding green energy in some way, shape, or form. Just to start, I want to address the issue about consensus. The scientific community believes that climate change is real and largely caused by human activities such as burning fossil fuels and deforestation. Climate change is complex and multifaceted, but it is a global issue that requires a multidisciplinary approach. Physics provides the fundamental understanding of how energy is transferred and transformed in the natural world, and this understanding is essential for comprehending the causes and the consequences of climate change. Physics is especially suited for evaluating the effectiveness of different strategies for mitigating and adapting to the impacts of climate change. The link here is to the organizer that goes along with this video guide. You can download it to use when taking notes by either printing it out in handwriting, or you could just type right into it. Energy is usually what we mean when we say electricity. Electrical energy is a form of energy that comes from the movement of tiny particles that you know are called electrons. These electrons are found in atoms, which are the building blocks of everything around us. Let's review some basics about circuits. When we want to use electrical energy, we need to create a flow of electrons through a series of conductors, like metal wires. We do this by connecting these wires to a power supply, like a battery or a generator. The power source causes the electrons to move through the wire, creating an electrical current. Current is the flow rate of charge, or how many charges pass a point in each second. Voltage is the amount of energy carried by each charge. When you plug a device into an electrical outlet, you are connecting them to a source of electrical energy that is generated somewhere else and transported to our homes or buildings. When we talk about electrical power, that's the rate at which energy is transferred or consumed per unit of time. 1 watt is equivalent to 1 joule of energy per second. In practical applications, electrical power is often measured in kilowatts or megawatts or even gigawatts, where 1 kilowatt is 1,000 watts and 1 megawatt is 1 million watts. The amount of electrical energy consumed over a period of time is often measured in units of kilowatt hours, kWh, or even megawatt hours, MWH. So what's electromagnetism? Well, that's a fundamental force of nature that deals with the interaction between electrically charged particles. Electromagnetism is not directly related to climate change, but electricity is generated through the conversion of other forms of energy, such as mechanical, thermal, or chemical energy, into electrical energy. This conversion process involves the use of generators, which are based on the principles of electromagnetism. So if you watch this animation, I'll click it a bunch of times, you can really see how spinning that magnet spins, we spin this coil here within these magnets, right? So you have this magnetic field, you turn the coil of wire here within that magnetic field. The magnetic field actually causes the electrons to move in the coil, and that motion of electrons then generates the current. Can you imagine if you had many coils of wire and really strong magnets, you would generate a really big current, and that would allow you to then power other devices. You can have really strong magnets here. You can change the number of coils. You can change the rate at which you're turning that coil. All those things will influence the voltage and the current that you create with your particular generator. So generators use the principle of electromagnetism by spinning the coil of wire inside the magnetic field. The spinning motion itself generates an electric current in the wire, which can then be used to power electrical devices or be sent through power lines to provide electricity to homes and businesses. Generators can be powered by various energy sources, such as fossil fuels, nuclear reactions, or renewable sources like wind or water. How does a coal-fired power plant work? Well, they pulverize coal It's then burned in the boiler to produce high pressure steam. So that's here. The steam is directed to the turbine blades. These then spin. It drives the generator here, which then converts this rotational energy into electrical energy. The steam, having given up its energy, is then condensed back into water, returned to the boiler to be heated and turned into steam again. The electrical energy produced by the generator is sent through transmission lines to power homes and businesses. This process is known as thermal power generation, and coal-fired power plants are just one of the most common types of thermal power plants. Natural gas-fired power plants and oil-fired power plants work in a similar way to coal-fired power plants, but they burn natural gas or oil instead of coal to produce heat. But you can imagine that no matter what you're burning out of those, you're generating all sorts of CO2 emissions, and those things are not good for our environment. Nuclear power plants use nuclear reactions to generate heat instead of fossil fuels, so they don't emit CO2, although the rest of the plant is not dissimilar. One strange vocabulary word that you should be familiar with is a quad, which means a quadrillion BTUs. A BTU is a British thermal unit. It is not metric, right? A quad is a quadrillion, or 10 to the 15th British thermal units, which is about the energy equivalent of 8 billion gallons of gasoline. We use this term to compare different sources of energy and their contributions to the overall energy mix, so it may come up on various graphs and charts that you look at. But now let's dig into the part that I'm really excited about, solar energy. It's a really important and growing source of energy, and it does not have the same type of energy emissions that fossil fuels do. Solar power is seen as a clean and renewable alternative that can help reduce greenhouse gas emissions and mitigate climate change. It's not 100% perfect, of course, but it's reliable and affordable, with access to people who have limited access to traditional power grids. The principle of solar energy not only relates to the fundamentals of energy conversion and thermodynamics, but has real-world relevance in terms of the global energy landscape and the impact of climate change. It also offers a wealth of opportunities for fun and engaging experiments, which is important to me, and we're going to do some cool projects. From building and testing solar panels to designing solar-powered vehicles or calculating the efficiency of solar energy systems, I'm hoping you gain some practical skills and insights into the science behind one of the most exciting and promising sources of energy for the future. So I'm going to give you like a really brief history lesson here. In 1939, French physicist Alexandre Becquerel discovered the photovoltaic effect, which is the basic physical process that underlies solar cells. In the late 1800s, an American, Charles Fritts, created the first true solar cell using selenium, but it had an efficiency of less than 1%, not very practical. In the early 20th century, Einstein published his theory of the photoelectric effect, which explained how electrons can be ejected from a material when it absorbs light. More about this later, but it helped lay the foundation for the development of modern solar cells, which didn't happen until the 1950s when Bell Lab developed the first practical solar cell. This paved the way for the space race as NASA began using these 6% efficient solar cells to power satellites and spacecraft. Solar technology has continued to improve with increasing efficiency and decreasing costs. It's one of the fastest growing sources of renewable energy, with installations around the world producing gigawatts of electricity. This chart from NREL shows solar irradiance across the US. Solar irradiance is the amount of solar energy that hits a particular area over a certain amount of time. In this chart, the areas that are colored dark red have the highest amount of solar irradiance, while the areas that are colored light yellow have the lowest amount of solar irradiance. We're not in a great place in the world, right? In New Jersey, look at that. So if you look at the chart, you can see that the southwestern part of the United States, like Arizona and New Mexico, have those highest values of solar irradiance, while the northeastern part of the United States, where we are, have the lowest values of solar irradiance. This means that the areas in the southwest are better for generating solar energy than the areas in the northeast. This chart can help us understand where it's best to place solar panels for generating large quantities of solar power. By placing solar panels in areas with high solar irradiance, we can generate more solar energy and make better use of those renewable resources. Before we go on, we really have to understand this idea of light intensity. In physics, intensity is defined as the amount of energy that passes through a particular area in a given amount of time. It's essentially a measure of how concentrated the energy is in a particular region. We can use it in terms of sound or light, right? Intensity is directly proportional to the amount of energy passing through an area and inversely proportional to the size of that area. This means that if the area is smaller, intensity will be greater, and if the area is larger, intensity will be lower. Mathematically, the formula for intensity is intensity equals power over surface area, and power is energy over time, so intensity is energy divided by surface area times time. So the smaller the area over which the energy is spread, the greater the intensity of that energy. So if you take a beam of light from a flashlight and put it onto a small spot, the intensity is much greater, and we see that as brightness. Our eyes are very sensitive to this brightness. This is an inverse square relationship because it's divided by area, which is distance squared. So let's apply that. If you look at this map, you can see it's a picture of the Earth, and there's 5 arrows showing the direction of the sun's light. The arrows show how the sunlight hits the Earth at different angles depending on where you are on the Earth. And the more oblique or angled the sunlight is when it hits the Earth, the larger the surface area it's covering, right? And that happens the further away you are from the equator. So that means that the same amount of light that's coming from the sun is spread out over a larger area, which makes it less intense. So if you're at the equator, the sunlight hits the Earth more directly, more intensely. This is because the equator is at a right angle to the sun's rays. This is why places near the equator are generally hotter. That's what we sense. So the angle at which the sunlight hits the Earth affects how much energy is received in a certain area. The more direct, the more energy it receives. This is important for solar power because solar panels work best when they receive direct sunlight. And you can do that by changing the angle of the solar panel to a certain extent. The amount of energy that the solar panel can collect depends on how much sunlight there is. If you look at the graph, the x-axis shows the months of the year starting with January and ending with December. The y-axis shows the average amount of energy measured in BTUs, or British thermal units, that strike each solar panel in a month. You can see that the highest bar is in June, followed very quickly by July, and it means that on average a solar panel can collect the most energy in those months. The lowest bars are in December and January, which shouldn't surprise you. It collects the least amount of energy at that point of the year. Well, that's because as the year progresses from winter to summer, the intensity of the light striking a house increases because the angle at which the sun's rays hits the Earth changes over the course of the year. In December, winter in the northern hemisphere, the angle is lower and the sun's rays are spread over a larger area, reducing the intensity of the light. In summer, the angle is higher, and it's more concentrated in a smaller area, increasing the intensity of the light. This occurs in June when the sun is highest in the sky and shines the most during the day in the northern hemisphere. This change in intensity affects how much solar energy can be harvested and converted into electricity by the solar panels. And notice that 70% of the solar energy comes in the middle 6 months. Photovoltaic cells are a type of technology that can turn light directly into electricity. We also call them solar cells. You may have used them before in small calculators. They're getting more and more popular because they can create a lot of electricity without making pollution. Residential solar power, in particular, is growing in popularity and dominates the increases in solar capacity in the US. So let's get into the physics. So sunlight is composed of photons. A photon is a teeny tiny packet of energy that makes up light. When you turn on a lamp, for example, the light that shines out of it is made up of a whole bunch of photons traveling in a straight line. Each photon has a certain amount of energy, which is determined by the color of the light it makes up. Photons are really important because they're how we see things. When a photon of light enters our eyes, it interacts with a special cell called a rod or a cone in our retinas, which sends signals to our brains that allows us to see. Without photons, we wouldn't be able to see anything at all. The photoelectric effect refers to the phenomenon where electrons are emitted from a material when light, in the form of photons, is shown on it. In simpler terms, when light strikes a metal surface, it can cause the ejection of electrons from the metal. This effect is due to the interaction between light and matter, specifically between photons and electrons in the material. The photoelectric effect is important in many technological applications, including solar cells, photodiodes, and photoelectric detectors. You may remember the reverse from chemistry. When an electron becomes excited, it jumps to a higher level, emitting a photon. We can see this emission in the form of colored bands or emission spectra, like I've shown here. A solar cell is made up of multiple layers of semiconducting material, typically silicon. The top layer of the solar cell is usually coated with an anti-reflective material to prevent the photons from bouncing off the cell's surface. A solar cell is made up of two different types of silicon, called p-type and n-type. These two types of silicon are created by adding impurities to pure silicon. P-type silicon has been doped with impurities that have fewer electrons in their outermost shell than silicon, resulting in a deficiency of electrons or holes. N-type silicon has been doped with impurities that have more electrons in their outermost shell than silicon, resulting in an excess of free electrons. We call those anions and cations in chemistry. When the p-type and the n-type silicon are brought together, they form a p-n junction, which is the heart of the solar cell. This junction creates an electric field that separates the positive and negative charges created by the absorption of photons. At the p-n junction, the free electrons from the n-type silicon migrate to the p-type silicon to fill those holes, creating an electric field. There are also metal contacts on the top and bottom of the cell that allow the electron current to be drawn from the cell and sent to the load. While I talk, you should navigate to the website shown here. Just type this into another browser window. I'm going to scroll through the infographic, but I highly encourage you to closely read and examine it at your own pace when I'm done. Solar cells are made up of silicon, which is a special material that allows sunlight to be converted into electricity. A solar cell has those two layers of silicon. One layer is called the p-type layer, and the other layer is called the n-type layer. There is also a metal conductor that connects those two layers. Silicon is used in solar cells because it is abundant, has a high melting point, and is a good conductor of electricity. The most important feature of silicon is that it can release electrons when exposed to sunlight. The p-n junction. When the p-type and the n-type layers of silicon are put together, they create this p-n junction. This junction has an electric field that separates the free electrons and the holes in the two layers. The electric field makes it easier for the free electrons to move towards the metal conductor and generate an electric current. Then comes sunlight. When sunlight enters the solar cell, it disrupts the bonds in both the p-type and the n-type layers of silicon. This creates free roaming electrons and holes in both layers. These free electrons are attracted to the metal conductor, and the electric field of the p-n junction helps move the electrons in the right direction, creating an electric current. And then what happens? Solar cells generate a direct current, electricity, DC, which is different from AC or alternating current that we use in our homes. So to use electricity generated by solar cells, you need something called an inverter that converts DC to AC electricity. Then we can use that to power our homes or businesses, or even it can be sold back to the grid. We have spoken about efficiency in this class recently. When you have a process already in place, you put a certain amount of energy in and get a certain amount of energy out. For example, in a combustion engine, you burn gasoline in a chemical reaction that produces a certain amount of energy. In return, only about 20% of that is converted into kinetic energy to get your car moving. In general terms, efficiency refers to the adoption of technology to get more energy out of that system. If you use an electric car, which is 85% efficient, you're getting a much greater energy output. And even if some of the electricity is generated from non-renewable sources, it's still greener than a combustion engine. You can look at some of those resources at another time. Solar panels are almost never used individually, but wired together in a sequence to amplify their power. The largest solar array in the US is located in Nevada. It has 9 million panels. Its annual net output is 1,348 gigawatt hours of energy, as compared to the Hoover Dam, which is hydropower, that's only 1.25 gigawatt hours. Solar panels are wired in series to increase voltage. The voltage of each panel adds together to form the total voltage that the array produces. The current remains that of the lowest possible current produced. This is why all of the solar panels have to be identical so that they all produce the same current. There are some uses when solar panels are wired in parallel. When a single panel has the voltage that you need, but you want to increase current, it's appropriate to wire it in parallel. So if you wire 4 10-volt, 2.5 amp panels in parallel, the voltage of the system remains 10 volts, but the amperage increases to 10 amps. Often in a solar array, there's a mixture of series and parallel. The major challenge to solar power comes from storage. Refrigeration changed how people consumed food, allowing them to store it before eating. Energy storage can revolutionize how we use energy. It lets us produce clean energy when it's cheapest, store it, and then put it back into the electric grid when it's needed. Using storage in conjunction with solar and wind energy helps ensure that energy is available when we need it the most. For example, when it's a rainy, cold winter day. This is an area of much research and continued innovation. Lastly, read these 4 questions. Choose one, or more if you want, and write your response in your notes. Please be as detailed and specific as you can, and we'll talk about this more in class. I hope this was an interesting investigation to you, and if you have more questions, please jot them down, and we'll talk about them when we meet in class next.